Usang muri after muri. Then that comes.
It's okay.
My name is Bashar Ali and my topic of presentation is oscillating circle. Now before coming to the topic, let me explain something behind how these new ideas and new topics came into being because these all are related to geometry. And as you know that geometry actually traces back from old, it's a very old concept, geometry. And you can understand by this that 3000 BC old concept, these ideas and concepts are. Geometry, I'm talking about geometry. 3000 old BC means that even the born of the prophet Jesus, 3000 years before the prophet of the born of the prophet Jesus. Now coming back, what is geometry now? Geometry actually is the study, the branch of mathematics that deals with the points, angles, and lines. This is a formal definition, or what you can say is the definition of geometry, that the study of angles, points, and lines. Now, the actual development and the actual things that happened in the 17th century, where the great two scientists, one named Sir Isaac Newton, you all are very much aware of his name, Sir Isaac Newton. The other one is Gottfried Leibniz. These two scientists actually they developed a new subject called calculus in the 17th century, and from then on actually there was a direct need to find out how these curvatures, how to find the arc length of a plane curve. And because of that, the definitions of nowadays we are studying curvature and osculating circle, osculating plane, torsion. So it traces back the history from their 17th century, Sir Isaac Newton and Leibniz. Now, and that was actually the starting point of differential geometry as well. And what is differential geometry? Actually, differential geometry is the branch of mathematics that deals with geometrical figures, surfaces, or curves with the help by using calculus. And by using calculus means the derivatives, limits. By using all the calculus things, we apply that on the geometrical figures, and that new branch we term nowadays is called differential geometry. So from then on, the history traced back to their 17th century, where the concepts of curves, curvatures, that was rarely needed at that time, and Sir Isaac Newton and these others combined and gave a new concept to the world about. And later on, actually, a lot of work was done by Monge, another scientist who has done his work in 19th century. But the founding fathers, you can say, of the differential geometry are Isaac Newton and Sir Gottfried Leibniz. These were the founding fathers. Okay, coming back to the main topic actually here, let me discuss about the curvatures. So what is curvature and what is curve? Curve actually, you can simply say that excluding the straight line, you can say that a geometrical figure having bending. For example, we have a geometrical figure having bending, then it is called a curve. I'm just talking about excluding circle because straight line. Straight line is a specific type of curve, but not in that sense. I'm excluding the straight line here. Then more the geometrical figure having bending. Any figure which have the bending thing in itself, you can say that it is a curve. Now, curvature. The amount of curvature is actually the measurement of bending that a curve has. How much the curve has bent. This has come into the consideration of curvature. And curvature actually now curvature, how to find that this curve has such a how much curvature. For example, we have a curve simply such type of figures we have. these are different geometrical figures, and as you can see, everyone has difference in their bending. You can see the figure 1 has less bending as compared to this, and this as compared to this, and this as compared to this. This has the greatest bending. Now, greater the bending, greater is the curvature. This is a simple concept. The amount of bending in a curve is called curvature. You can see that this will have less curvature as compared to this, and as you move on, this curve has a lot of curvature, meaning the bending in itself is very large. But the idea of curvature now links with the radius of curvature. How to find the radius of curvature? So actually, radius of curvature and curvature has inverse relation. I'm going to write a relation here. Radius of curvature. It has an inverse relation with the curvature of a curve. Meaning, what does this relation mean? Now, we can say that this radius, the curvature, greater the curvature, meaning radius of greater the curvature, the radius will be less, and vice versa. If the radius of the curvature is greater, meaning the curvature of that curve will be less. You can see here the curvature bending, meaning simply I can say bending of a curve. The curvature of this geometrical figure is less. So from the formula here we have the radius of this curvature will be greater. And actually you can take any point on this curve. For instance, we take 2 points and draw a circle. This is obvious that the circle of this, the radius of this curvature will be greater as compared to this. As you move on, you know what? This bending of two claws, we can say, these two claws becomes closer and it allows less space for a circle to draw, and because of that the radius will definitely become lesser. And moving on and on, you can see you will get less radius. So greater the curvature, less will be the radius of that curve. Or actually, geometrical representation of finding the curvature of a curve, I have a representation. We have plane here. This is a simple curve, and for example, we take any point on this curve. And actually, yes, in the incoming study, you guys will get the idea. But just to be sure that curvature of a curve at any point is different. If you take a point here, the curvature of a curve and the radius of the curve and the center of the curvature will be different as compared to this, as compared to this, as compared to this. Because at every point the curve behaves differently. You will get different results about their curvature, about their radius, and about their center of curvature. Now, for example, let me take a point P here and draw a tangent line to this point. By drawing the tangent line, this tangent line will make an angle theta, or you can say psi. It's up to your choice. On the tangent line, draw normal. Now, what is normal line? A normal vector or a normal line is that line which is perpendicular to your tangent line. This line is perpendicular to this. You can say that this is a tangent line. Another neighboring point we take is Q. Draw another tangent line to this one. Here you will get with x-axis the angle psi plus del psi, and the bending angle here we have del psi. Okay. Now let for example we have this point A. This AP distance, the distance between A and P, we name this as S. And first thing I forgot, actually we draw the tangent line. Now also draw another normal line to this tangent line. And the intersection of these two normal lines, we name them as N. Now, as you can see, these two lines which intersect each other at this point, this will also make another angle. We named it angle psi. And the distance between this P and Q is del S. Now what I'm trying to give you the idea from this figure. To understand the curvature idea, that how much the curve has, how you can find the curvature of a given curve by just simply representation. Now you can see the distance between A and P is S. We have the distance between P and Q is del S. Angle P and Q, this one, equals del psi. Now, as Fayaz explained in a different way, I am going to explain a different way. When Q approaches to P, when Q approaches to P, that point N, this line we call this C. Then point N approaches to C. This is also called center of a curvature. If you approach this viewpoint from this position to this, you can see, if you drag this point to this, automatically this line will also becomes in contact with the C line. If Q approaches P, then point N will definitely approaches to C. And because of that, angle psi, delta psi will also approaches to 0. There will be no angle left between this P and Q angle will become 0. This will definitely approach to 0. And so is this distance. This distance will also be approaches to 0. Now, the limit del S approaches to 0 to del psi divided by del S equals to d psi divided by ds, which is equal to K, meaning kappa. When del S approaches to 0, so the ratio between this del psi and del S will be equals to d psi divided by ds, which is the required curvature of the given curve. Actually, the actual definition which given by Sir Isaac Newton in the 17th century about the curvature of a circle is that the rate of change r derivative of the tangent to the curve as curve as one moves along the curve. Let's write the definition so you will get the idea. The definition was given that the rate of change or derivative of the tangent to the curve as one moves along the curve. The derivative, meaning the tangent line, at that time in 1760, the Isaac Q, the concept about the curvature, in simple words, this means that this the angle between this tangent line and the ratio, okay, the tangent to the curve as one moves along the curve. This definition becomes that was at that time. Now the definition of this becomes equal this. Why? The tangent line, the rate of change of the rate of change means the derivative of the tangent to the curve as one moves along the curve. If you take the point this, sorry, curve is there. If you take the point this or at any point, so the curvature will be different at different points. Now, osculating circle.
Bridge lagi. Bas kalah ka. Ramadan here.
Talking about the osculating circle, actually the word osculating, that came from the Latin word oscular, which means to kiss. Now what does this mean? Actually, if you see a practical example, I can give you a practical example of osculating, how this osculating circle works. For example, a car is moving on a bendy road, and we saw these a lot in the movies. That if a driver tries to stop his vehicle, plugs or locks his the moving vehicle, the car tends to move directly at one point. Now that point where the wheel starting to rotate and try and make a circle, that point is actually called the kissing point. You can see here that in the osculating circle, the circle will be towards the normal side. Any side where the concave side of the curve, the oscillating the circle will form. If the point moves along the curve, you will show that where the concave side the circle will be formed. That was okay. The circle and the curvature, the oscillating circle, the The curve and the circle tangent will be the same here in the oscillating circle. You can see that this P point shares the similar point where the curve we have the tangential point of the curve and the tangential point of the circle is the same. This is one point. The other one is, as we know that I have explained that the radius of the curvature will be reciprocal. Will be reciprocal to curvature of the curve. So this was just simple explanation.
Thank you.
Any question? Okay.
Stop it.
Mansur.